so we should be able to have a better interaction. And this is a fresh topic, so not unlike last topic where I had nothing to do, and it's a relatively simpler topic as well. So we will be talking about clustering, and let's first see what is clustering pictorially, and then I'll try to give up my own spices to the problem statement. So if you really look at the blue data over here, so let us say that I have a data which has two features, F1 and F2. By now you know very well what does the term feature means. And in my example, I say that what I do is that I take in a course and I evaluate the students on the lab, as well as I evaluate the students in terms of theory. So this becomes the lab marks and this becomes what is the theory marks. And I see a natural distribution like this. So what does that really mean? That there are certain students who are both good in the lab as well as they are good in the theory, so they are probably my A candidates. Surprisingly, because the question paper was something like what I might say is binary, either questions were too easy or too difficult. There were students who were neither good in theory nor in lab. So some of them are just doing okay in lab, and some of them are doing bad in lab. Some of them are doing okay in theory, and some are bad. But then overall, the marks in neither lab nor in theory are okay. The theory is still a little bit okay. And then, of course, there are certain students who appear to be doing very good in theory but very bad in lab, and that's something practical these days. All the students use ChatGPT in all the assignments, and in the lab test, they are like, "What? We really need to program, and I cannot use ChatGPT." So good enough in theory, but then lose a lot of marks because nothing is working. Now, if I look this kind of data, this makes in three clusters where this type of students are very much alike each other, these type of students are very much alike to each other, and these students are of course very much alike to each other. And again, a practical example that I'd probably like to meet the students of these three different types to know what their problems are and how can I improve the performance of these students and these students. Now, of course, the practical problem is I do not know how many clusters they exist. Luckily, here I can plot it up. But for a general problem, there would be, in today's world, hundreds and thousands of data items in high dimensional spaces, and within which I need to understand how many data clusters exist, whether clusters exist or not. Not all problem has clusters. Like in reality, the total theory marks and lab marks both are mostly continuous. We never practically get clusters. It's problematic that we have to fit them into clusters called A neg, B, and B neg, where practically there may be no clusters. So I need to find out whether there are such natural clusters or not, how many such natural clusters are there, where are those natural clusters, and so on and so forth. That is my problem about clustering. And of course, it would have been easier if this would have been the very first topic that I would have said, but then currently a problem that I face is that you have already learned something, that supervised learning. So I could use something like a naive base and learn the distribution of these three classes. So the means of the three classes and the standard deviation. What could also happen is that I could take in a multi-layer perceptron that learns this decision boundary and classifies the data anything at one side of the decision boundary. I could use a SVM that learns this kind of data. And of course, I was previously doing decision trees. So it is possible that I first partition the data over here, in the left part partition it over here, in the right part partition it over here, and I get these decision boundary and I get these classes as well. So we have all studied uh, these things in the name of supervised learning, they are much more advanced. Why do I go classic and I say that it's clustering? Now, it appears that supervised learning is the solution to all problem, and practically so many times I see students trying to justify that unsupervised learning is better than supervised learning, even if we have labels, which is not really the case. I have a personal anecdote over here. So I deal with a lot of data for the real problems that I have. So I mean, I'm a robotician. I'm not a machine learning expert. God knows how I'm being called over here. My domain is robotics, and a practical problem that I do face is that I can collect a lot of data. So for us, whatever images are recorded by a self-driving car, that's a data. I can put a dash cam. These days dash cam are both very popular as well as extremely budgetary, so a lot of people put them. So I can just take videos while you drive, and I have a lot of data available with me. Similarly, I could make a simulator, and my self-driving car or robot could just work randomly, wander aimlessly and take images. So you've got these wonderful software these days which can tell you, okay, you describe your room, they will create a DALE kind of image, and not only a DALE kind of image, they'll also have the 3D effects where you can navigate around. I can do all those things. In fact, today I can use ChatGPT to generate a lot of synthetic data around of what does a self-driving car look like and all. The problem with all this is that, of course, I mean, if I go the classic sense, which is supervised versus unsupervised, I don't have the labels to that. I don't know what are the objects lying in that. Somebody will have to annotate that up, and I do not have the semantics of it. I do not know what is contained in those objects. So for any machine learning problem, I don't have the target. And again, to give you a practical example, so we are doing a project wherein we had to record the similar data. We drove some vehicles, we placed some cameras in the city, we flew some drones, and in 2 days we collected like gigabytes and gigabytes of data. So, and honestly, we were not doing anything. We were just sitting, sipping coffee, sipping tea, having chai pakora at the different places in the name of research. The cameras were doing the job autonomously. So I can record the similar data by using the Institute CCTV camera as well. So there's no dirt shortage of data. What's the problem is the shortage of annotations, and that's where you of course get unsupervised learning technique like the clustering. Now, I mean, again, I have a personal anecdote before I take up this problem a little bit into the core algorithms. As a robotician, my personal anecdote, sometimes what happens is even more weird. So sometimes nobody knows what are the labels. So you go to the annotator and you say, annotator, annotator, I'll give you 30 lakh rupees. I have a lot of government money, and please annotate it for us. The annotator will tell you, sir, we are the best company in annotation. Please give us the label classes. And you will like, what? Do I need to give you label classes as well? I don't know. As an example, I mean, I like YouTube, so I like watching videos. I need to describe the different types of videos, educational video, cooking video, but I don't know how many type of videos exist. I don't even know that. I am this thing. I make robots work around kitchen, homes, offices, warehouses, factories, outdoor, indoor, every place. I don't know what kind of objects exist. I don't have an exhaustive list of them. In our case, it's more, I mean, just because I'm currently dealing with this problem, I can say this with a personal anecdote as well. So we recorded a lot of data, and we wanted to say, is the driver following traffic rules? Is he not following traffic rules? Is he driving safely? Is he driving aggressively? Is he trying to have imitate some kind of driving behavior? We go to the annotator. Annotator says, okay, give us what is safe, what is not safe, what is aggressive, what is cautious, what are different types of driving behaviors. And we are like, no, but we are not supposed to do that. We don't know how many behaviors exist. So the problem is that most of the times, not only is it that we don't have the annotation, but we don't know what are the output label classes as well. So, I mean, a classic example would be this workshop is being organized amidst the result declaration section, and my Excels are ready. So, luckily, I have got a lot of tabular data. Now, I would like to know how many types of students exist: students, skillful but lazy, very studious but this thing extremely careless, something like that. I don't know how many types of students exist. I want my data to tell that over to me, so that I can see how the teaching and learning experience can be better for my students in the next semester. Now, I don't know how many classes exist. I absolutely have no idea how many classes exist. I don't know the class specifications. And therefore, I made very bold statements last time when I said that for tabular data, random forest is better than any other technique, including deep learning, including CNNs. I make another bold statement. Every advancement in so-called AI, ML, etc., that you see, it's only been because of unsupervised learning, because a lot of textual data was available from the web with no annotations. A lot of video data was available from video sharing website with no annotations. Thanks to some of you people for putting videos online, including I think this video is going to come online. A lot of book data was available with publishers making digital copies of the book, and it's all unsupervised. Nobody had real labels to it. So practically, it's easy today to record data. It's impossible to get annotations because number one, for any practical data, we have annotators who take in a lot of money and they require specifications which are impossible for us to give. With that anecdote, I go completely down. I completely come down into what is specifically required as a part of this course. And once we have done all the lower levels of abstractions, once we have potentially understood what the algorithm is, once we are comfortable with it, then maybe towards the end, I will again give you a little bit of personal anecdotes and tell you some interesting stories about where we people use in robotics the k-means clustering algorithm. But getting up to the hardcore algorithm. So my problem is, as of now, at least to show it simple, I can only take two features, F1 and F2. So let's take the same example, theory marks and lab marks of my students, so that I can get typical types of students and call them to the office. They are the real student leaders, not the way we currently do voting. So somehow I know that there are three clusters, and it could be a wild guess that I know that there are three clusters, or sometimes it's like that I know that I need to call these students and to discuss cases with them. So one discussion is gonna take 20 minutes and I can only devote 1 hour. So I know that I can talk to a maximum of three students, and that's why there's three. Sometimes there are national number of clusters. Sometimes you have limitations about how much data you can study in detail. And that's again where unsupervised learning and supervised learning, clustering and supervised learning, they differ. So supervised learning gives you a label. It's a class one. It's a entertainment video. It is the case where the vehicle is looking at a supermodel in front, or it is the case where the vehicle should slow down and speed immediately. But unsupervised learning only gives you cases with no output, so you're supposed to analyze those cases, see what is in those cases, and by chance, if you know what happened in any one of those cases, generalize to the same thing happening in all the cluster, all the members of the cases. So here, luckily, I somehow knew that there are exactly three clusters. It's currently a limitation, A, because there are naturally three clusters, and secondly, because I have the bandwidth to only study three cases in detail. So I make random guesses, like the first cluster is far away from any data point, so it's a very bad guess. I say this is my first cluster, it's not even correct. I say this is my second cluster, it's not even correct because it's again far from any data. And then I say this is the third cluster, it's far enough from anything, so it's not even correct. So let's say the same example that somehow I want to talk to the students to discuss what grades should I give to the different types of students. So I have this problem that I need to cluster them into three different categories, and therefore these are the three student leaders virtual that I make. These are representative of one type of student, the second type of students, and the third type of students. Now what happens is that I'll see which student belongs to which cluster. So let us do it for one student over here. That's one data item over here. So I measure this distance, and I measure this distance. So let the distance be D1, D2, and D3. And currently what happens is D1 is less than D2 and it's less than D3. So this student says that, okay, the professor gave me three leaders. It's like the girls in social media, sometimes they don't actually exist. There's another algorithm which enforces the leaders actually do exist. So this student says that I look more like this person, although the distance is extremely large, but this person best associates itself to this person because these two are very far off. These two are very far off. It's like me doing my PhD, so went into a lab. So there were some this thing people from all around the world. I did from the UK, so I'm like, okay, these people are too much different from me. Their native language is English. I don't even follow them up. Those are heavy meat eaters, and then these are the people who are from multi-ethnic background, non-English speaking. So I'm more like those people. It's still very different, but I better connect with those people. So every student is finding out the leader out of the three leaders that it associates more, and this guy says, "This is my leader." So let's choose leader for everybody. This is the closest to this for this little thing. This distance is too large. This distance is too large. So I'll actually go with this distance. And similarly here. This guy is interesting. So this distance is actually almost equal to this distance, but I think this one is a little smaller. So this becomes a marriage. So every student actually selects one of the leaders to which it most responds to, and every student will be associated to that leader, and that's just recoloring the data, saying this set of people associated to this cluster head, these set of people associated to this cluster head, and this set of people associated to this cluster head. It's blatantly wrong. So I mean, it's blatantly wrong, and that's terrible cluster. So if I look at this output currently, so for every point in space, I find out which point in space is closest to which cluster, and therefore if you take anything in this region, it's closest to this cluster. Anything in this region, it's closest to this cluster, and any point here, it's closest to this cluster. So that's how my natural clusters are divided right now, and they are erroneously wrong. They are horribly wrong. But let's get back to this picture again. So it's the same picture that I show you. Uh, the previous step, what I did was I, as a professor, gave three cluster heads. I gave in three student leaders. Unfortunately, they were virtual student leaders. To the student, and student picked up their leader. Now I do the reverse process. And in the reverse process, I say that let the student, let the leader be more or less closely occupied to the student. So previously the student selected the leader, now the leader will adjust according to the needs of the student. So let's look at this student leader, which was made by me at a position that was given up by me. and it says my distance with the first person that I represent is D1, its distance from the second person I represent is D2, the distance from the third person I represent is D3, the distance from the fourth person I represent is D4, and similarly D5, D6, and D7. So this is the distance that I have from the data that I represent. I represent x1, x2, x3, x4, x5, x6, and x7. Now what I will do is, and I'm cluster center number one. So what I'll do is the cluster center number one, the new position will be equal to the arithmetic mean of all the data that I represent. So, and xi belongs to cluster number one. So I say in this case, my cluster number one new position will be equal to x1 is what I represent, x2 is what I represent, x3 is what I represent, all the way up to x7 is what I represent divided by 7. So I'll place myself somewhere in the arithmetic mean of all these. Now I have approximately calculated this one up. So there's more data on the left, there's only two data on the right. So the right data is mostly what we will call as an outlier, and the mean will shift more towards where majority of the data is. That's how arithmetic means work. If two of your students get 1 crore package and 10,000 students get 5 lakh package, your mean will be closer to the 5 lakh than the crore. So my mean will be closer to this thing, and I move this mean over here. And similarly with the others, so there's more data over here, there's little data over here, so I'll move more towards the more data as a result of arithmetic mean. And there's more data over here, there's no data behind, so I'll move over here for sure. And this data is lesser than the one at the top, so I move a little bit on the top. So I get an updated picture. So the orange one had moved down. The orange one had moved down. The red one had moved top right. The red one had moved top right, and the green one had moved over here on towards the right. The green one moved here towards the right. Now things did improve because I started out with something that was terrible. I mean, the three student leaders looked nothing like the student that they represent. And now, at least they look something like the student that they represent. At least they look something like the student that they represent. So the leaders have adapted to the students. And I say that this entire process is what is in a repeat mode. So now what will happen is every student will associate to one of the leaders. So this distance is smaller than the other two distance. So this marries this leader, this associates more to this leader, this associates more to this leader, this associates more to this leader, and this associates more to this leader. Now this is the interesting one. This guy was actually married to this person. So this guy was like this thing, a staunch follower of political party A. Let's make it a political and not name the party A. And suddenly, what happens is that this new party, which has come up, its leader looks more like this person. So this person is like, hey, I associate myself to this person much better. So the old party has broken. It's just that you find a leader who you connect to more and a new leader whom you connect to more. So, I mean, funny example. So, I said that during my PhD, I was trying to find out people whom I associate to more. So, probably the non English speaking nations were a better candidate. But after I joined the lab and after many of us joined the lab, so some of this, I mean, this thing, students starting behaving more like us, toned down the accent, took interest in talking about the cultures, blah, 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 so we could associate to them more. So we're like, okay, now we'll start, I mean, this thing, talking to you people, and we'll start getting associated to you people as well. So Similarly, over here, that this person who was previously associated to this political party will now get associated to this party because the leader is closer. And again, this person was associated to this political party will now get associated to this party because the leader is closer. And similarly, these two will change their parties. So students change the leader whom they associate to because as the leaders move, they get increasing distance from the older ones and the decreasing distance from the newer ones, and the students will always get associated to the leader whom they associate more, who is closer, who's more like them. In this case, this is what happens. So these are the new marriages, and now you can see the clusters are a little bit more obvious. So the clusters are a little bit more obvious, and everything is married to a leader which is very close by, and everything wonderful seems to happen. Let's recolor this up because the green was the old political party, orange is the new political party. So let's make that orange, and similarly, the political party will change from purple to green over here, and the political party will change from orange to purple over here. So this clusters looks good. It's a complete repeat process, and in this process, what I will be doing is that the students have selected a new leader. The leaders have new membership. So this orange now decides D1 from a new X1, a D2 from a new X2, a D3 from a new X3, a D4 from a new X4, a D5 from a new X5, a D6 from a new X6, a D7 from a new X7, and it takes in an advantage, it takes in a new calculation that C1 updated is equal to X1 plus X2 all the way up to X7 divided by 7. So it'll actually come around somewhere over here. Let's see if I have a picture. Yeah, I have a picture over here. So this moves somewhere here, this moves here towards the mean, and this moves here towards the mean. Uh, if I happen to repeat it one more time, if I just happen to repeat it one more time, you'll see nothing will change. These will be the cluster marriages. Every student will be with the same cluster as before. So no student gets a better cluster. So no student gets a better cluster, and the average of this will turn out to be this, average of this will turn out to be this, average of this will turn out to be this. And luckily, it is a better picture for me because these are my cluster boundaries now. This is cluster number one, this is cluster number two, this is cluster number three. How did I do that? If you take in any point, the distance from this cluster is smaller than the distance from this cluster, and for the boundary points, the distance from this cluster is the equal to distance from this cluster. So a person on the boundary line can actually join any party. He's at the decision boundary, at the inflection point. So these are the clusters that I get. So I have this region which is completely cluster number one. Currently the cluster is only here. This region which is cluster number two. Currently the cluster is here, and this region has the cluster number three. Currently the cluster is this, and that is where we say that the algorithm has converged, because no matter how many times I run this algorithm more, I will get no change in cluster membership and no change in the position where the cluster heads lie, and therefore I say my clustering is what is complete. So let's look at the steps once very briefly. So let's look at the steps once very briefly. Now, I said somehow I decided that there will be exactly K clusters. So as of now, it could either be the number of students whom I can interview. In fact, another example of clustering is you go on any website, let's say Flipkart, and you search for something that you need. Let's say that you want to buy a new pair of trousers. So the first results that come in are actually, you don't get exactly the same trouser 10 times, and you get different types of trousers because Amazon would like to know what are your preferences. So they are internally kind of doing clustering, and then they are managing how many results to show on the first page. So sometimes it's limitation of the human about how much things do I want to study in a greater detail, and sometimes is something different. So sometimes what happens is that I have a natural cluster and I need to take exactly the same cluster size. So I initialize some cluster heads. This could be done as bad as randomly. So just take some cluster heads, like I made it 3 class monitors. I had urge to make 1 class monitor for each type of student, but I made it just 3 random class monitors, and those class monitors did not actually exist physically as well. Then I asked the students to associate to one of the leaders, one of the class monitors, one of the provided sample type of student, and that's what all the students did. And I told all the class monitors, the student leaders, that these are the people in your clan. Now the leader looks at it and says that, hey, this does not look like a clan. The people of my clan, the people of my tribe, the people of my cohort, the people of my group are a lot different from me. It's my duty to blend in. So the class monitors, the class leaders say that let me just blend in. So they move towards the centroid of this data, they move towards the arithmetic mean of this data, they move towards the center of mass of this data point. So they look more like them. But then as a result, what happens the moment the class monitor and the class leaders they change their positions, something weird happens, and that something weird is that the students who were initially closer to the clusters, closer to the monitor, closer to the group leader, now started to feel difference, that this person became more like somebody else, and now this guy doesn't represent me. So the monitor changed to better blend in. As a result, the tussle between some of the students increased. Some of the students who were previously close to the monitor are now no longer close, and some other monitor is close to them. So the students change the people whom they idealize. The students change the people whom they like. They change the cluster. And as a result, the membership of the leader, the membership of the cluster head also changes. And this person is like, okay, now let me blend into the new people whom I have. This loop will converge when neither students will be able to find a better leader, nor the leader or the cluster head will be able to find a better student. And that is what I say that my learning task is complete. Uh, I started with saying that there are 3 clusters, and people believe that there are 3 clusters, but I could also say that 6 clusters are also okay. So one, two, three, four, five, six. 6 clusters are also okay. And why is that a problem? So first, let's use a metric that decides how good a cluster is. A cluster is good when it has a small intra-class variation. Okay, this one is closer to this. This will get married to this. This will get married to this. I'm just marrying clusters. So every data goes to the closest cluster. This one, I think this gets this one. So if I say this is D1, this is D2, this is D3, and this is D4, and this is the cluster C1. So the intra-class, the intra-class separation for the cluster C1 is D1 plus D2 plus D3 plus D4. Intra-class separation. The inter-class separation is this distance, the distance between this class and this class, this class and this class, and so on and so forth. So a clustering technique is good if it has a small intra-class separation and it has a high interclass separation. So I need to minimize the intra-class separation. The class monitors, the class leaders should look more like the people whom they represent. Everybody should be able to very closely associate themselves to the class monitors or the class leaders or the clan leaders. And no two clan leaders must look very similar to each other. No two clan leaders should look very similar to each other. So my interclass separation should be very high. That's a good clustering technique. So if I do one thing, I plot the intra-class distance, which is these distances, the summation, by increasing the number of clusters. Of course, the distance would decrease. The distance would decrease. And why would the distance decrease? Because in the worst case, when k is equal to n, so every student is a student leader. For a batch of 10,000, I made 10,000 leaders. So everybody is the leader of himself. All my intra-class separation becomes exactly zero because everybody is representing himself or herself. So as k increases, this distance tends to decrease. In the worst case, when k is equal to n, it actually becomes zero because the distance between every leader and the people whom is represent, which is the person himself, is always zero. That's what's happening these days. Everybody wants to be a leader. Nobody wants to be led. But the problem is, I only want to follow the leaders on social media, listen to them, talk to them. Now, because everybody is a leader, I want to talk to all of them. Gone are the days when in a class you could tell people to select leaders, and we as faculty would only talk to the leaders. Now, everybody is a leader. So, office timings are ideally going up like anything. Now, this is also the utility. What you see, this is what's called as a knee. And the property of the knee is that if I increase K, I have too many people to talk to, too many cases to analyze. However, the utility is not that large. The utility is very small, like from the knee to here. This is the only utility. This is the only drop in distance, but K substantially increases. So this is ideal number of clusters. And we set k to these many number of clusters. To repeat, if I take k larger than this, there's no problem, but I'll have to talk to more people. If I use k less than this, there's no problem, but then the people within the cluster would be very different, and the student leaders would be like, see, there's too much of variation between ourselves as well, so I cannot generalize anything that I say. uh, a little thing that is problematic about the k-means clustering, and let's discuss a little thing before I give you my ending anecdotes as well. So k-means clustering has two problems. The first problem is you don't get the same output everywhere. So let's say I have a data, and over this data, I run the k-means clustering. My clustering can get stuck at what is the local minima. By local minima, I mean that the choice of the random clusters is such that you have a better solution possible, but it's not able to probe in, it's not able to blend in, it's not able to do the assignments which are much better. And therefore, sometimes people suggest to have a multi-starter. That's a solution to everything. K means clustering. So I just run the algorithm multiple times and take the best of it. So this is a handleable problem. You don't get this problem in small dimensional spaces. You only get this problem in the dimensionality of the problem, when the dimensionality of the space is humongously high. And over there, we of course do have a major problem about this local minima. But then there's a greater problem associated with the k-means clustering, and some people really hate k-means clustering because of it. So let's see what the problem with k-means clustering is. say I have exactly the same data which is over here. So I have exactly the same data which is over here. I can see that there are three clusters that I took. Normally they went exactly where they were supposed to do. However, many people who do Exceling and tabulation would know sometimes instead of 1.5 we enter 15. And the student who should ideally be here because of this gets over here. And this is what's an outlier. Now, the closest to the outlier is this data cluster center, and this cluster center will move over here. Nobody can stop it. And it will keep moving over here because the distance is very large. As a result, you will only get practically two clusters for this regions, and one cluster head will be at outlier. The problem is sometimes we don't enter 1.5 as 15. Sometimes we are even more worse than that. Sometimes instead of theory in lab we will enter 1.5 as 15. I can get another cluster over here. So I deal with robotics again, trying to get into personal anecdotes. So uh, too many problems, too many noises. So uh, the image data that we take, we have to sometimes take it at the sun, and sun glares. So the RGB distribution that we expect is not the one that we get. We use some extremely expensive depth sensors, and sometimes what happens is that either because of fog or rain they'll have short reflection, or sometimes they would have interference and we'll get something completely different. The natural data has too many clustering, and in fact we talked about annotations. To avoid giving money to annotation companies, sometimes we add, sometimes we use students as annotators. They will look at a car and they will annotate it as a person. So now the machine learning technique is suddenly looking at the car and it's being forced to say that it's a person because the annotator did a terrible job. So the problem with k-means clustering is that it cannot handle outliers. So the k-means clustering, it absolutely cannot handle outliers. I'm a little uh, guy who looks at the positives out of the negatives. So I look at the positives out of the negatives. Believe me, if you have to remove outlier, one of the techniques that you can use is k-means clustering. So perform k-means clustering with a very large number of cluster heads. Look at the cluster heads which have too small membership, remove them as noise and repeat. So in the hindsight, k-means clustering is also one of the algorithm that can do outlier removal. It's not the best outlier removal algorithm because we did not study the complexity of k-means clustering, which is larger than all the other clustering algorithms, which should have been in the curriculum. So that is really one of the issues that is associated. So I think I'm almost up on time. So I have some 5 minutes. So let me give in another personal anecdote into uh, something that would be at least of interest with slightly more advanced audience. So let me get it a little bit of a personal anecdote to that one. Uh, this time I don't go lame by saying that I have a tabular data, and because I have a tabular data, so uh, random forest is what is the best for me. So I get to the exact data that I talked about. So we recorded a lot of data, we recorded a lot of videos, we recorded a lot of trajectory data to look at, I mean, what does a self-driving car really see, to look at what type of movements does a self-driving car have with respect to of its neighbors and all. So to make it simple, let's say that I have a lot of image data, and image data is not the tabular data. Both random forest as well as k-means clustering can only be applied to a data which has the smoothness constraint, similar data looks similar, and image doesn't have that up. So what do I do is I apply a model to have low dimensional features over it. So I could do autonomous driving over it, but then I'll need a lot of label data set to train this one up, and I cannot apply clustering because the local smoothness constraint at the image level doesn't exist. And therefore, of course, the very famous thing that we have is that you use another model to reconstruct the data, and you get your reconstructed image back. Now, even though it's supervised learning, but basically from an image I'm learning features, and from features I'm learning image, so the output will be exactly same as the input, and that's what's the autoencoder. So remember I said that my problem is I've got a lot of high dimensional data, I've got a lot of image data that we've recorded that up. So I cannot do autonomous driving because I don't have the labels. This option doesn't exist with me. So this option is what is gone from me. So I will learn an autoencoder model that maps the image to features and features to the reconstructed image. But then the problem is that what do I use it for? What do I really use this data for? Because the one thing that I'd like to do is to look at the data in bare naked eye and to get some insights over it. Now, most of the data that we have looks very similar. Like mostly cars travel straight, they look at straight roads with some traffic elements. So most of our data is like this. I want those near collision cases, I want those corner cases, I want those difficult cases, I want those sharp turn cases, I want those cases where a beautiful girl comes in front of the car and the driver is like, wow, and it's a Bollywood movie experience. That is like 0.0001% of the data because, of course, the supermodels that exist, they don't usually come out on road and we don't get their data. So I want to do those cases. So what I'm going to do is to those get those cases is I'll take these features and I will apply k-means clustering on these features. So today, if you work in biomedical engineering, you have a lot of X-ray reports of cancer, a lot of biopsies, a lot of MRIs, or you work in video where you have lots of images of different traffic patterns, or you work in 3D perception, you've got a lot of 3D images taken by moving people cameras. Getting images is easy. The first thing that we do always after we get the image is we need to cluster them up. I cannot apply clustering on raw image because of this problem. There's no local smoothness assumption. So I'll transform the image space. I'll transform what we call as the image space into a latent feature space using deep learning technique. Of course, advanced courses or maybe a follow-up of this course will talk about it. And here is where I will use a k-means clustering. And at least one of the things that you can immediately do with k-means clustering is that whenever you record the data set, the publication houses want the most distinctive image set, 20 or 30 image in the paper itself. More than that, you don't have space in the paper itself. That also goes on GitHub, YouTube, and all. So k-means clustering gives you the most distinctive 20 or 30 images that you can put on your paper, that you can put at your GitHub, that you can put on your YouTube. That tells how diverse the data set really is. So with this, I would again get into the conclusion mode. So We started out by saying that, okay, practically the problem always is that it's very easy to record too much of data for any real life problem that you have. You don't know the kind of student data that you are dealing with on an everyday basis without realizing that. The problem is, in most cases, I don't know what to do with the data, what is the output of the data, what is the class of the data, and I don't know how many natural cluster the data forms. So, in data analytics, in every real life application situation, one of the essential thing that we do right now is we cluster the data, and from the cluster we select the cluster heads, and then we look at the cluster heads to decide the problem that we need to solve, the labels that should exist, the number of natural clusters that should exist, and so on and so forth. So for clustering, I start off with just randomly giving some cluster heads, making random people as leaders and asking those leaders to select their kind of people. The people select the leaders as the leaders move, and the leaders blend into the people that they represent, and this equilibria about the leaders blending in with the people and the people connecting to the closest leader that they see, that's a very small process, that's a very short process, and that is what is essentially the k-means clustering. And I think this thing the point that I have been making around over here is that K-means is by far not the best clustering, not in terms of complexity. It has problems in terms of noises, but then it's also the most convenient technique to use. Though, yes, I mean, if you could remove outliers, if your data is already limited, then K-means becomes one of the essential and one of the easiest techniques that you can use, that for which code is just 10 lines and you can directly apply to the data set and get early results. And I think I'm happy to conclude this one on time. If there are questions, I'll be happy to answer.
Hello, participants. You have time. Please ask your doubt, your query. You can type here in the chat box. Okay, I think no doubt is from participant side. So,
Happy to
okay.
conclude. Thank you, people.
Thank you, sir. Thank you very much for coming and accepting our invitation. Thank you very much, sir.